Okay, it's starting to record. So thank you all for coming in for today's debate. And thank you, Sasha and Steve calling in. Sasha calling in from Hawaii, Steve calling in from a very interesting place. You may mention that if you want to. So on the left in the slide, we see Sasha Krot. He's faculty at University of Hawaii at Manoa. He's interested in astrochemical and cosmochemical problems related to the solar system formation, and work on also isotopic anomaly and chondritic meteorites, isotopic chronology, etc. And the other speaker, Steve Desch, is a faculty at School of Earth and Space Exploration at ASU, our neighbor in Arizona, and works on the modeling of the star and planet formation using data from meteoritic and planetary science, and especially interested in the origin of chondrules and meteorites. This is both of your interests. There are a lot of interests. I just had to pick a few. So now I think, let me see, I can go to the next slide. So just one slide about background before we start. There's long-lived radionuclides that has half-life of about a billion years, like the well-known uranium-238. Short-lived radionuclides that you will hear a lot about today, that has half-lives about 250,000 years. And ejection of short-lived nuclides, radionuclides, that was made in stars to ISM. What do they do? Which one can eject those radionuclides? So red giants can be Wolf-rayet stars or can be supernovae. And these SLRs inherited by the solar system birth are now decayed, except few examples, like iron 60 at the seafloor from nearby supernovae. That was 3 million years. And so these short-lived radionuclides were abundant at the birth of the solar system, as you all know, and you will hear a lot about this. How can we use that to figure out the solar system formation? So today's debate, so Steve and Sasha will have some presentation back and forth. So Steve will first start introduction, and Sasha will have other introduction, and we'll talk about iron 60, aluminum 26, beryllium 10, and especially the question of inheritance, injection, and irradiation picture. So now I will stop sharing my slides so that Steve can share.
Okay, thanks. Yeah, thank you really a lot for hosting this, and I'm looking forward to it. I've been looking forward to it for a long time. I have strong opinions about each of these topics, as you might guess, and people may ask, who made you judge and jury? And in fact, I am a juror today, and I'm coming to you from the Phoenix Municipal Courthouse. This may be the first time this has ever happened in this debate. I don't know, but anyway, that's where I am, and it makes this whole thing legal. So let me make sure I've got my slides up, and I will share my screen and get started. Yeah, so let's see. Are you seeing my slides or my screen? Well, whatever, here it is. Yeah, so what I want to talk about are the origins of the short-lived radionuclides. Waiting for my slides to catch up. There we go. This, by the way, is the Crab Nebula, and this is a paper I was on. The big image.
So Steve, we are seeing the other materials in your background as well.
Yeah, we're seeing your desktop, including something about some faculty committee.
You
can't do all of it. So.
I'm gonna just go with it. It's okay. So okay. Yeah. All right. Okay, so what do short-lived radionuclides tell us about the birth environment of our sun? And astronomers, have this idea that we form near a supernova or something, but it's much more subtle and complicated than that. And there's basically 3 families of astrophysical models for where the short-lived radionuclides came from, and there's so many. I really couldn't do a good job of reviewing all of them, but inheritance basically posits that the radionuclides were already in the sun's molecular cloud, the long-lived, the short-lived, all of them. And probably these molecular clouds formed from gas that was enriched over generations of star formation in a spiral arm of the galaxy, probably. And it's, you can make simple models, and those references here cover those models. And they make predictions about how much you should have in the solar system. And the shorter lived ones decay pretty rapidly, and you don't have as much of them. Longer lived ones you have a lot more of. I want to note that during cloud core collapse, there's a lot of mixing, spatial mixing that goes on. And you would expect that the abundances of all of these radionuclides that were in the molecular cloud should be pretty uniform in the solar system if they were inherited from the molecular cloud. There's another class of models that is I'll call injection, where the idea was that a nearby supernova or possibly some other stellar nucleosynthetic event, but most likely supernova, injected material into the sun's molecular cloud sort of during the formation process, so there wasn't time to mix, or into the protoplanetary disk itself. And this has usually been invoked for two reasons. One is the idea that maybe there wasn't a lot of radionuclides at the very earliest stages of the disk, and you would need to inject them later. Or in the case of iron 60, one of these radionuclides, it would have to have come from a nearby supernova because there was just so much of it, was the idea. And my opinion about these models is that, because I've worked on them quite a lot, is that it's certainly possible to inject material into the protoplanetary disk, but it requires a special set of circumstances that makes it kind of improbable, and mostly because young disks aren't found that close to a star when it's about to go supernova. And then finally, it's possible that the radionuclides were not external at all to the solar system, that they were produced in the solar system. The sun, especially the early sun in its T-Tauri stage, had a lot of solar flares that accelerated energetic particles to MEV energies. When these hit other nuclei, you could transmute them. So you could produce radioactive elements this way. And there's been a number of models about this. I cite Ganell et al. 2001, for example. The tendency of these models is that they're really good at making beryllium-10, which is another radionuclide, for reasons to do with just the nuclear physics of it. And it would predict big variations in how much beryllium-10 different things in the solar system have. So these are sort of the classes of models. And to sort of judge these, we have to take a look at star formation and how that actually proceeds. So I wanted to give an astronomical perspective about this. Our Milky Way is a spiral galaxy, not unlike M51 shown here. And like all spiral galaxies, most of the star formation in the galaxy takes place in the spiral arms, these things here. And you can see that there's a lot of new star formation, a lot of bright luminous stars, blue stars here. And that's where most of the stars are forming today. The pattern that you see is rotating at a different rate from the stars itself. So in fact, stars are orbiting, the sun takes about 250 million years to go around the galaxy. The gas is orbiting much more slowly. This pattern speed is kind of moving more slowly. So the stars kind of go in and out of these spiral arms very quickly. And as they do, if they explode and eject material, they can contaminate the material in the spiral arms before they leave the spiral arms. And the opportunities to do this come from, there's a variety of stellar nucleosynthetic sources. You're familiar with supernovae, and any star more massive than 8 solar masses is going to explode as a supernova. If you're in the range of 8 to 20 solar masses, you'll probably explode as a type 2 supernova, and that takes as little as 6 or as much as 50 million years or so after the star forms. And this is an example probably of a 9 solar mass progenitor. And stars that are more massive than 20 solar masses, they will also explode as type 1b or 1c supernovas. They'll do that very quickly. They evolve for only 4 to 6 million years. But before they explode, they have this very energetic winds that take nucleosynthetic material away from the star. These are called Wolf-Rayet winds, and here's an example of a star that's not gone supernova yet, but will. And this material has been ejected. And this material is ejected like several solar masses, ejected at almost the same speeds as supernova. So it's like a pre-supernova supernova. When that star, a star more massive than about 20 solar masses, goes supernova, the central parts actually don't make it out. They tend to fall back on to a black hole. And so it's only the outer layers. So these are two types of end results of stellar evolution that can lead to stellar nucleosynthesis that can contaminate spiral arms. There's also, of course, red giant stars, there's novas, there's neutron star mergers, all these things contribute as well. So let's look at a star forming region. And this is a molecular cloud. And you see, like here at the very tips of these pillars, this is similar to the pillars of creation, but this is actually a different nebula, NGC 6357. But it's undergoing the same sort of processes. You have brand new stars. These are O stars, very massive stars that are actually, one of these is undergoing the Wolf-Rayet stage. It's transitioning to that right now. And these will go supernova in a few million years. And you have new stars forming here, all throughout these molecular clouds. And I point this out because, all these stars form together. These new stars that are very massive, that explode within about 5 or 6 million years, they will not have moved far away from the nebula. And so they have the opportunity to contaminate this molecular cloud material directly. And the longer it takes for a star to evolve, the further away from star forming regions it's going to be when it explodes. Wolf-Rayet stars and the stars that go supernova after the winds, the massive stars are very good sources of calcium-41, aluminum-26, and magnesium-53. These are all short-lived radionuclides. Not so much iron-60, and that's relevant later. So, so in these spiral arms, you have especially Wolf-Rayet winds, supernovas, and then you have this general galactic background of other radionuclides formed by other stellar nucleosynthetic sources. And finally, one other radionuclide, beryllium-10, is made not in supernovas, not very plentifully anyway. It's possible to have neutrinos make some, but mostly it comes from cosmic rays that hit oxygen atoms in the interstellar medium or in molecular clouds and swallow the oxygen nuclei from beryllium-10 nuclei. And these galactic cosmic rays are ions that are accelerated by basically supernova shocks. So you get a lot of cosmic rays where you have a lot of supernovas, and those are in spiral arms. And where they're produced, they tend to propagate about a kiloparsec, which is about the size of this circle. So in between spiral arms, you get less beryllium-10, and in the spiral arms, you get a lot. When you have all these explosions going on, there's a nice animation on Eva Stryker's webpage showing how you have supernovas going off and it's like popcorn, and the material goes up and it falls back down onto the galaxy. All this gas is mixing, and in spiral arms, it mixes very effectively on timescales of like 10 to the 8 years or so. So check out that animation if you go to her website. I want to show now if you do have enrichment of that gas and of molecular clouds, if it form from that gas in spiral arms, you can make predictions about how much of each radionuclide you have, and you can compare that to the amounts that we infer from meteorites. And Sasha is going to talk about how we infer how much of these radionuclides existed in the early solar system. But for now, just know we have measurements, and basically those measurements scaled to a prediction are kind of on this axis. And on this axis is the mean life of the radionuclide. And you can see there's a dozen different short-lived radionuclides, well, extending up to very long-lived ones. And for each one, this black curve is a prediction of how much there should have been in the solar system. It's a model from Ed Young, who's here. It's based on two parameters. You have two input parameters, which is basically how much do Wolf-Rayet winds contribute versus other sources, and how long does it take to mix that material back into new stars. And there's a residence time in this model of 140 million years, which is basically what we see in the galaxy. And this model needs Wolf-Rayet winds to contribute thousands of times more to that new material than other sources, which is a statement that Wolf-Rayet winds explode near star-forming regions. But if you make those assumptions, the black line is what you predict, and everything falls very closely to this line. So I think it's a very successful model. Now, I point out iron-60 here because if we assume that the iron 60 to 56 abundance was this low value of 10 to the minus 8, as it appears to be, then the meteoritic value lies right here, which is pretty much on the curve. But there is a lot of controversy, or there had been, that says it was much higher, 10 to the minus 6. Like there was 100 times more of this iron 60 at the birth of the solar system than we think today. And that would put you way up here, way off the curve, and that would demand a late supernova input. And it would demand a low mass star to eject that iron 60 and so forth. So that's one of the things we'll be talking about today. So to summarize so far, you have these three sorts of models: inheritance, injection, irradiation. Of course, they could all operate simultaneously. It doesn't have to be exclusive. I think it's pretty clear inheritance, just enrichment of molecular cloud material, is the dominant source of the short-life radionuclides. It pretty well explains almost all of them. But there could be contributions from injection, certainly if iron 60 has a high value, but not necessarily if it's at a low value. And maybe you do need it if aluminum 26 didn't exist in the earliest parts of the solar nebula, but if it was there, then you don't need injection for aluminum 26 either. And irradiation, we know there were solar flares and energetic particles. Do they actually have an impact on the material in the disk? Not necessarily, unless it shows that, unless you see the beryllium 10 was variable in disk material, then you would need to invoke some irradiation. And I think you probably do need it to explain some very late contributions of chlorine 36, but it's unclear. So at that point, that is the summary of the astrophysical models and what we need to know from meteorites to address which one of these is dominant or ruled out. And so Sasha's going to talk about meteoritic data now. But go ahead, Sasha.
So can you see it?
Yes.
Okay. So in order to address the initial abundances and distribution of these three short-lived radionuclides, aluminum-26, iron-60, and beryllium-10, we need to look at the older solids that formed in the protoplanetary disk. And these include refractory inclusions, if you would like to address aluminum-26 and beryllium-10, and chondrules, if you would like to address iron-60. And at first, I'll talk about chondrites and their components and what we can tell about origin and environment for the formation of refractory inclusions and chondrules. So this slide shows combined X-ray metal maps in magnesium red, calcium green, aluminum blue of 6 different meteorites from 6 different chondrite groups. And so based on mineralogy, petrography, and biochemical and oxygen isotopic compositions, so we currently defined 14 chondrite groups. And by default, we think that they all come from different parent bodies. So the important point is that calcium aluminum-rich inclusions are found in all chondrite groups. And after accretion, chondrite parent bodies experience some parent body processes like aqueous alteration and thermal metamorphism. And to emphasize the degree of processing of chondrites on their parent asteroids, we define them into so-called petrologic types. And with temperature increase and chondrites experience thermal metamorphism, so they go to high petrologic type. If chondrites experience aqueous alteration, they go to low petrologic type. And by default, chondrites of petrologic type 3.0 are considered the most primitive, so they largely avoided both thermal metamorphism and aqueous alteration. So each chondrite consists of 3 main components: refractory inclusions, which include calcium aluminum-rich inclusions and ameboidal aggregates. So on this slide, they look kind of bluish and greenish in color. Then chondrules, which look reddish on this image, and the fine-grained material that occupies the interstitial regions between these 2 main components. So this is a 3-oxygen isotope plot. Along y-axis, I plotted the ratio of O17 to O16 in the sample divided by the standard -1 multiplied by 1,000. And along x-axis, the same ratio only for O18. So on this diagram, all terrestrial samples plot along line with slope 0.5, which is called terrestrial fractionation line. And almost all solids in the solar system, they plot near this value. In contrast, the oxygen isotope composition of the sun, which is shown as a yellow star, deviates significantly from terrestrial value towards O16 rich composition. And it looks like all chondritic components follow slope 1 on this diagram, in contrast to terrestrial fractionation line. And so the significance of this slide is that if you look at oxygen isotope composition of refractory inclusions, they all have composition very close to the solar value. So on this graph, I only plotted calcium and Igneous inclusions from CR carbonaceous chondrites. And chondros in all chondrite groups plot near the terrestrial fractionation line. So the point here is that calcium and Igneous inclusions and chondros formed in isotopically distinct gaseous reservoirs in the solar system. So what we can tell about origin of refractory inclusions. On the top diagram, I showed the stability field of different minerals that condense from the gas of solar composition. So the most refractory, like corundum, hebonite, and the least refractory is forsterite and astatite. And on the bottom, at the bottom, I showed this magnesium calcium aluminum rich maps of different types of refractory inclusions that we find in chondrites. And if you look at their textures and mineralogy, we can divide them into 2 main groups. So one group, they represent objects that basically condense from the gas and subsequently coalescing together, aggregated. And so these are 3 bottom objects. And on the right is object that formed by melting of these condensates. So they're so-called igneous inclusions. So they put the point that irrespective of texture and mineralogy, all these refractory inclusions are surrounded by O16 rich forsterite, which, as I said, formed in the region where calcium and Igneous inclusions formed. So what it means that the processes that I invoke for the origin of refractory inclusions, like evaporation, condensation, aggregation, melting, they all happened in the reservoir where subsequently forsterite condensed. And because forsterite has condensation temperature around like 1300 degrees Kelvin at pressure of about 10 to minus 4 bar, it means that refractory inclusions formed in the gaseous reservoir with very high ambient temperature, above 1300 degrees Kelvin. And many people think that this region was exposed to irradiation by solar energetic particles, but this is a controversial topic, as we'll discuss today. But because calcium and Igneous inclusions, and so the region that had high ambient temperature, had gas of solar composition, was O16 rich, and was exposed by radiation. So it's kind of easy to assume that this region was very close to the protosun. But refractory inclusions are found in all carbonaceous and non-carbonaceous chondrites, also found in cometary dust. So the significance of these observations is that after formation, the refractory inclusions must have been removed from this region and subsequently dispersed throughout the protoplanetary disk and accreted together with chondros and matrices. Another important point is that the refractory inclusions, or calcium and Igneous inclusions in all chondrite groups, are surrounded by multi-layered rings, the so-called Vauquelin rings. And these rings have exactly the same oxygen isotope composition as the host inclusions. And most people think that these rings formed in the same reservoir where refractory inclusions formed. And Some inclusions, as I'll show on the next slide, experience remelting during condor formation. And in most cases, these reams were melted and destroyed. And the bottom right slide shows refractory inclusion, which I labeled as CI inside the chondrule, which I label CHD. And this CI is surrounded by a single layer of spinel, whereas the inclusions on the left shows that after spinel, we have melite and pyroxene. So what it means that melite and pyroxene layers were melted during incorporation of this inclusion into the chondrule. So what we can tell about chondrules? So chondrules formed by melting of isotopical diverse solids, including CIs and ameboidal aggregates and chondrules of early generations. And during repeatable localized transient heating events in different regions of the protoplanetary disk, inside and outside the snowline. So on this slide, I summarize the major characteristics of the formation regions of refractory inclusions on the left and chondrules on the right. So refractory inclusions formed in the disk region with high ambient temperature, higher than 1300 degrees Kelvin. Chondrules formed in regions with low ambient temperature, typical less than 650 degrees Kelvin. So refractory inclusions formed in the gaseous reservoir that was O16 rich, and this gas formed by evaporation of disk regions with approximately solar dust to gas ratio, which is 1 to 100. Whereas chondrules formed in an O16 depleted gaseous reservoir, and this gas formed by evaporation of dust rich regions of the disk, where dust to gas ratio was 100 to 1000 times solar. So refractory inclusions formed under highly reducing conditions, whereas chondrules formed under highly oxidizing conditions relative to the solar value. Refractory inclusions formed in disk region with low ambient with low pressure. Chondrules formed in region with high total pressure. During formation of CIs that were melted, they experienced melt evaporation and fractionation of isotopes, so-called mass-dependent isotopic fractionation. Whereas in chondrules experience gas melt condensation and almost complete exchange between the gas and the melt. As a result, there is no mass-dependent fractionation effects in chondrules. And refractory inclusions were exposed to radiation by solar energetic particles, like to explain beryllium-10, but again, this is a controversial topic, but we think that this region was near the protosun. So chondrules formed in dust-rich disk regions of the disk. They were shielded from radiation, and we think that chondrules formed throughout the protoplanetary disk. What we can tell about formation timing. Refractory inclusions are the oldest solids formed in the solar system, and so the only data that exists for their dating suggests that CIs that were dated formed 4567.3 million years, and it is considered to be cosmic chemical time zero for the origin of the solar system. And formation of refractory inclusions may have lasted less than 0.5 million years, but it's model dependent, depends on the interpretation of aluminum-26 CIs. So chondrules may have formed as early as refractory inclusions, but the formation of chondrules lasted the entire life of the protoplanetary disk. So this is how we define the age of our protoplanetary disk, which is about 5 million years. So CIs after formation must have been transported outward to accretion regions of chondrites and comets, whereas chondrules appear to have accreted locally into planetesimals. I think that's all I have for the introduction.
Okay, so shall we go to the questions for each?
Yeah. So should I share my slides with Iron 60?
Right.
Sasha has to stop.
Yeah, Sasha could just, yeah.
Okay.
Yeah.
There we go.
All right. Let's see if this works again. Okay, now you're just seeing the slides. That's good. So I think Sasha and I are in agreement that Iron 60 and what we can measure from data is the ratio of Iron 60 to Iron 56, the nucleus there. We agree that value is low at the 10 to the minus 8 value, and there's a lot of literature, a lot of measurements. For example, Tang and Dafa, pretty definitive, 1.0 10 to the minus 8. There has been controversy in the past, especially when it was first measured, that it was at 10 to the minus 6. And the way you measure it, because it's all gone today, is to look for excesses of the decay product, which is nickel 60. You look for excesses of nickel 60 relative to nickel 62 versus the ratio of iron to nickel in different samples within a meteorite. And you want to look at something that is ideally, all of them shared the same isotopes originally and should all have the same nickel 60 to 62 ratio. And if it turns out they don't, and that correlates with iron, then you can say that some of this nickel 60 was due to decay, like iron 60 into nickel 60, sorry. And so if you see a line, then you have what was called an internal isochron. And unfortunately, a lot of the data that are out there, especially derived using SIMS, secondary ion mass spectrometry, is kind of noisy like this. It's been disturbed. Some of the isotopes have moved around. A lot of the assumptions you make to get at these values don't apply. And in fact, and you can see the reduced chi-square is 10. It's a really far fit from a line. So you can't really infer a value. And in fact, this paper showed that using a very sophisticated technique, resonance ionization mass spectrometry, that they showed exactly how SIMS measurements were giving you the wrong answers. So the ones that are right are the 10 to the minus 8 values, and these higher values aren't right. And there's also these bulk isochrons. You can just melt down like an entire iron meteorite and measure its isotopes, and that's what this is, and you get 1 point. And if you knew what its starting composition was, you could look at the variation in the nickel 60 isotope on this axis versus the iron to nickel ratio on this axis. Different isotopes, the same idea. And if you knew it started here, then you could draw a line, you get a slope, you would get the initial value of iron 60. But you have to assume a starting composition. They assumed in this paper by Cook et al. A CI composition, but they really should have picked a CV composition. A CV chondrite is a better fit for the nickel isotopes, in which case it would be here, and the slope would be consistent with 10 to the minus 8. So I think the meteoritics community is pretty certain, but not entirely certain, that the iron 60 value is low, 10 to the minus 8, and that does not demand a nearby supernova. It's consistent with just galactic background. But that's what I want to say about that. I don't know if Sasha wants to add.
Yeah, could I have a comment?
Go ahead, please.
Yeah, the main kind of reason of controversy in the community, although the data that are shown on the left on Steve's slides indicate that there is no correlation between the excess of nickel 60 and iron nickel ratio, still the data show excesses of nickel 60. And so the group that produced this data argues that it is a disturbed isochron, but it must have started with the high iron 60, iron 56 ratio. And so they basically put the upper limit on the initial abundance of iron 60. And this is where this is right now, the issue is unresolved. So why they observe excesses, it's not clear.
Right, that's true. I mean, they list a slope here, and the slope is certain, and it would certainly be high, except this MSWD shows it's not a line, that the data are not explained simply by decay of iron 60. There's something else going on, and we know it's disturbed. So it's just not reliable. You can't infer a 60-56 ratio.
So if I may ask a question, where is the 10 to the minus 8 coming from? Because I don't see it here in these figures for the iron 6.
Sounds like Ilaria.
Hi.
Yeah, there's data like this. I didn't put them up, but like papers like this, they have clean isochrons and they infer values like this. And when you have clean isochrons, those are the values they infer almost universally.
So if you have to get the range of it, what ranges are kind of accepted? 10 to the minus 8, plus minus?
20 or 30%.
Okay, thank you.
I mean, let me add. I think there is only one internal isochron for one chondrule was measured by ICP-MS, by Tang and Tofas. So they produced very low initial ratio. And then there is one paper by University of Chicago group who used another technique called DREAMS. And so they analyzed the same chondrule that was measured by Thales, that is the graph showed on the left. And they also inferred very low initial ratio. But again, they were only able to put the upper limit. And so the upper limit on the isochron for this chondrule is consistent with lower limit of the paper by Thales. So again, this is the problem. This is why the issue is not solved.
And I'll add that in looking at the iron-60 abundances of bulk chondrites, kind of a similar sort of situation to this, those are consistent. Like if you're trying to make it concordant with other systems, it's very consistent with a low value, a little less than 10 to the minus 8, and not at all consistent with higher values for iron-60. So no, not an internal isochron, which would be the gold standard, but the weight of the evidence is really strongly in favor of a 10 to the minus 8.
So do you have any question from the audience? Are there any other question about iron-60? All right, then I think we should move on to the next one. Is it aluminum-26?
Yeah, well, yeah.
Let me see, there is one comment from Francois Tissot. There are more isochrons in Tang and Tofas 2012, including bulk isochron of HED, internal isochron of,
Yeah, thank you, Francois. Yeah, there are, it's more than just one inclusion. And yeah, I think there's a preponderance of evidence, 10 to the minus 8.
I think I saw just a hand from Curtis. Do you still have a question, or would you like to wait?
Yeah, I'll just add a quick question regarding the value for iron-60. And it seems like the uncertainty surrounds whether or not the robust isochrons are showing us a lower limit, or if they're actually showing us the real true value. And I guess my question to the two presenters is, what does the community have to do to resolve that issue as to whether or not we're getting a lower limit, or are we actually getting the real value such that we can lay this issue to rest once and for all?
I think it is convincing to me already, so I don't know. I'm not a meteoriticist. Sasha knows.
No,
Sasha?
I mean, ideally, we need like several internal isochrons for chondrules to have some statistics to see whether maybe we're able to resolve the initial abundance. But it looks like it cannot be done by SIMS. So for some reason, all SIMS data show excess of nickel-60, although in most cases, it's not correlated with high nickel ratio. But the reason for that is not clear. So basically, we need to rely on RIMS measurements. That's my feeling.
Okay, just one more question. Ching Zu In.
Yes, I guess the question that I have is regard to that Cook et al. Study. Steve said 2D parent should be CV chondrite instead. Are there reason for that? Do we know that 2D is a carbonaceous iron meteorite parent body, or
Yeah,
I don't remember.
So there were 2 iron meteorites in this paper, 2D and another one. Both of them are in the CC family, and they argued it should be carbonaceous chondrite precursor.
But how do I know it's a CI versus CV? Are there like isotope anomaly suggest a linkage, or what?
I don't think they could justify picking CI. I think they were wrong to do that. And in fact, if you look at the nickel isotopes that they measured, it's a better match to CV.
Okay. Thank you.
Okay, thank you. So I think we should move on. We still have 2 more questions to go. So
Yeah.
Steve, yeah.
Okay, I'm gonna, oh, Sasha's gonna go.
Can you see this?
Yeah.
Okay. Okay, so we are switching to element 26. So element 26 is a short-lived radionuclide that decays to magnesium 26 with half-life of about 0.7 million years. And so on this graph that I took from the FAST paper, I showed how aluminum magnesium isochron diagram works. So on the top left slide, so let's say that we have some bulk chemical composition of that is represented by yellow star that has certain aluminum magnesium ratio and magnesium 26-24 ratio. And this material experience some sort of chemical fractionation. So the easiest way to understand like evaporation and condensation, where phases with different condensation temperature condense from this gas, and these phases will have different aluminum magnesium ratio, which are indicated by different symbols on this diagram. And every phase after formation will start, aluminum 26 in each phase will start decaying with different rate depending on the aluminum magnesium ratio. And at the end of decay, all these symbols will plot along a single line, which is called isochron, and the angle of this line corresponds to the aluminum 26-27 ratio. And the magnesium 26-24 ratio at time 0 can be inferred from this, where this isochron intercepts y-axis. So now let's make the situation more complicated. So let's say that the same kind of reservoir that is represented by yellow star evolves before chemical fractionation. So before this chemical fractionation, aluminum 26 will decay, so magnesium 26-24 ratio will increase, and then you will have chemical fractionation. And so initial magnesium 26-24 ratio will be slightly elevated relative to the earlier composition, and the isochron at the end of the decay of aluminum 26 will have slightly shallower slope. And so if you compare these two different isochrons, so two lines with different slope, we can calculate the age difference between these two chemical fractionation events, which is indicated by the expression at the bottom of the slide. So where the canonical aluminum 26-27 ratio comes from? So the highest precision measurements were made based on bulk isotopic measurements of calcium aluminum rich inclusions and ameboid dolomite aggregates. But basically, this bulk composition represents chemical fractionation of the gas of solid composition. And the slope of this isochron is 5.25 times 10 to minus 5. And the intercept of this isochron, which is magnesium 26-0, expressed in parts per million, it has symbol mu, is minus 16 ppm. And so if you compare any other isochron with this canonical isochron, we can calculate the age difference between formation of another object and formation of calcium rich inclusions, which, as I already said, that they're all the solids formed in the solar system. And the uncertainty on this isochron is extremely small. It's only 0.002, and which in terms of time corresponds only 2,000 years. And so originally when this paper was published, so the conclusion was that duration of the formation of CIs lasted 2,000 years. But again, it's model dependent because it depends on the assumption of uniform distribution of aluminum 26. So another way to obtain aluminum magnesium isochron is to analyze individual minerals within individual inclusion. And the easiest way to understand if you have igneous inclusion, where all phases crystallized initially with the same initial magnesium isotopic composition. And again, the phases which crystallize from the melt has different aluminum magnesium ratio. In this case, it's like malite and spinel. And after decay of aluminum-26, we produce an isochron. And this isochron is called internal isochron. And so this isochron on the left has slope 4.9 times 10 to minus 5, which is very close to the canonical value. And the graph on the right shows internal isochrons in CIs from different chondrite groups. As you can see, they have a larger spread than 002 for the bulk model isochron. And based on the spread of aluminum-26-27 ratio and CIs from different chondrite groups, so the conclusion was that, at least by now, that formation of CIs lasted at least 400,000 years. There is another data set that was published in 2021, I think, or 2020, by the same group that produced the first bulk model isochron that was based on the measurements of refractory inclusions from CV chondrites. So in this case, they acquired the data for refractory inclusions from another chondrite group, CR chondrites. And what they found that the bulk magnesium isotopic compositions and the magnesium ratio of these refractory inclusions plot on a different line with the same slope, 5.2 times 10 to minus 5, but with intercept, which is close to minus 100 ppm. And so there are some CIs that have much lower initial aluminum-26-27 ratio and much more negative intercept with the y-axis, which corresponds to the initial magnesium isotopic composition. So the conclusion of this paper was first that formation of CIs was episodic and possibly associated with outbursts from a accreting protosun. So CIs formed close to protosun and were distributed to out disk, either via stellar outflows or turbulent diffusion, with progressively decreasing transport efficiency. And so both mechanisms, the stellar outflow and turbulent diffusion, predicts that CIs that formed at the very beginning of the solar system formation will be transported to the largest radial distance from the sun. And on this diagram, they assigned like CI and CH chondrites further away from the sun than CV and CR CIs. But if you look now at refractory inclusions from primitive chondrites, internal isochrons, we find occasionally that some of the CIs have much lower than canonical aluminum-26-27 ratio. These are three inclusions which mineralogical look very pristine, and the formation sequence of minerals for these inclusions is very similar to what is predicted by condensation from the gas of solar composition. And all the CIs have all-16 rich isotopic composition, so it means that they formed in the same reservoir where all other inclusions originated, near the protosun. But the isochron on the left is only 1 times 10 to minus 5, and two other isochrons show no resolvable excess of magnesium-26. So now I added to the original diagram with internal isochrons data for CIs that have much lower than canonical aluminum-26-27 ratio, which are shown by gray diamonds. As you can see that there is a big spread in the initial aluminum-26-27 ratio. And so there are different ways to interpret this. It's either heterogeneity of aluminum-26 or result of thermal processing. So if CIs recorded heterogeneity of aluminum-26 in the formation region, then, some people argue that aluminum-26 poor CIs predate formation of aluminum-26 rich inclusions. So then late addition of aluminum-26 is required before or during collapse of the protosolar molecular cloud. And as already Steve summarized, so low initial abundance of iron 60 with some caveats in the solar system precludes solar supernova origin. aluminum-26. So aluminum-26, according to so aluminum-26 must have been ejected by wind from nearby Wolf-Rayet star, and it took some time to homogenize aluminum-26 in the protoplanetary disk. And this homogenization is recorded by formation of CIs with different initial aluminum-26 to NCI ratio. So according to another idea, aluminum-26 was inherited from the protosolar molecular cloud and was uniformly distributed in the disk. But there are several carriers of aluminum-26 and magnesium isotope completion. So these are the graphs from Larson paper that I showed before. And according to this paper, there are three different dust that contributed to the solar system, like old dust, new dust. So both types of dust lack aluminum-26, and freshly synthesized dust that contributed to aluminum-26. So if you mix these three components and homogenize, so the distribution of aluminum-26 will be uniform. But if you somehow preferentially destroy one of the components, you can produce heterogeneity. So they call this process unmixing. So according to this process, so in principle, you can explain differences in initial aluminum-26 to NCI ratio between the CIs. But they made one step forward. They said that aluminum-26 in the solar system is heterogeneous as a result of this unmixing. So that's all I have for aluminum-26.
Okay, so we have only like 7 minutes left, but Steve, I think we should show your plot. Yeah.
Yeah. So just leaving these up, I think this latter idea is the most promising. I think there definitely were heterogeneities. I do not think they're spatial. I think every cubic meter of the solar nebula was like every other cubic meter of the solar nebula. And I don't think they're temporal. I don't think there was a time when there wasn't aluminum-26 in the solar system, and then there was. I think what you're looking at is a chemical heterogeneity, that you have different things in the solar nebula. Some of them did have aluminum-26 and some had aluminum without aluminum-26. And different reservoirs of pre-solar grains might do that for you. And we're trying to develop that model ourselves. I'm going to put up my screens now. Start sharing mine. And I'm starting with the assumption that aluminum-26 was very homogeneous from the time zero. If you look at different samples, like these are different achondrites, and we're looking at bulk abundances of achondrites. These are volcanic ones, these ones with the green checks. And all of the isotopes should have been well mixed and achieved isotopic closure at the same time, which means that you can date them using the technique Sasha described for aluminum-26. If you know the initial abundance of aluminum-26 and you measure it in a chondrite or an achondrite, and you see less, then you can infer how long after time zero it took to form. And you can do that using aluminum-26, those are the red ones, but also manganese-53 decays, and if you know the initial abundance, you can get that. Hafnium-182 is another radionuclide. If you know the abundance and you measure it, you can get an age from that. And finally, we have the lead-lead system, which also gets you an age. And we, this is recent work, we tried to see if the ages match, because they should match for volcanic achondrites if the assumptions are good, which is the assumption of homogeneity. And this model has 4 parameters and it fits 40 pieces of data. And for the volcanic achondrites, all the ages match. And one of the free parameters here is that the lead-lead age is 4,568.65 million years. It's not 4,567.3. What lead-lead ages of CAIs are measuring is not time zero, and I can talk about that. But this model, fits all of these data pretty well, and it fits exactly the ones that have to fit exactly, which is volcanic achondrites. So this is really strong evidence that aluminum-26 and actually all of these radionuclides were homogeneously mixed throughout the nebula at time zero. I will allow that there are a few samples, Sasha pointed out a few like these that are show very little evidence for any aluminum-26. Like there's firm upper limits on how much they could have held. They're all associated with the most refractory phases, hibonite, corundum, grossite. And there must have been places in the solar nebula where pre-solar hibonite, pre-solar corundum grains are the only grains that survive in that region. And so if you have pre-solar grains without Alanine-126, they may form larger aggregates. And I think that's what we're seeing when we see the plaques, when we see the hibonite-dominated fun CAIs. You're looking at some very rare, very small, very unusual samples that are looking before the time of the solar system that are recording the pre-solar stage. But other than that, no, the nebula was spatially and temporally homogeneous, and it does not demand a nearby supernova or production within the disk. It's all consistent with inheritance from the molecular cloud.
Okay, thank you. So now I think it's 1 o'clock, so some people will have to leave. So I will actually ask you to answer some question in the chat. You can click and answer your question. You can edit it later and update it. But I think I would like to go briefly, at least for the beryllium-10. And then for those of you who can stay here longer, can stay. Otherwise, I would post the recording in our YouTube channel, which I gave the link from chat. So beryllium-10, I think discussion will continue. And if you can stay, please do. If you can't, please come back and check on that. And please do the survey if you have time. Thank you. And then we'll continue. I think, Steve, you will continue from here, right?
Sure, yeah.
For beryllium-10.
So basically,
and we can get questions as well from the audience.
Yeah. If beryllium-10 was not homogeneous, if different samples recorded different values of beryllium-10, that would demand irradiation within the solar nebula, probably. And the question is whether they are or not. If you do have irradiation, the models aren't developed really well yet, but the suggestion is something like at least 25 or 50% of CAIs would have to record values that were different from the mean. And the mean is about 7 times 10 to the minus 4. This is a nice compilation of data from my collaborator, Emily Dunham, and this is in a paper coming out in May. And what you see is that the beryllium-10-9 ratio, it looks as if it's very variable, but in fact, the colored ones, there's something distinct about them that makes them unreliable probes of what the solar nebula had at time 0. These are because these CAIs experienced irradiation onto the parent body, which produce new isotopes, which messes up the analysis. And these guys are fun CAIs that were disturbed at a later time in the nebula in distinct ways. And but if you just restrict your attention to the ones that you have great confidence are probing the beryllium-10 abundance in the solar nebula at time 0, they're all consistent with 7 times 10 to the minus 4. At least 95, probably 100% of those with good isochrons that you have no reason to doubt probe the nebula at time 0. And I think Sasha agrees that most do, but maybe Sasha thinks that there's a slightly larger number that are inconsistent with this value, but I don't think he'd agree it's anywhere near 25 or 50%.
Okay, I mean, since Steve has this slide on the screen right now, you see that one of the problems is that, yes, you know, the so-called fun CIs, so fun means fractionation and unidentified nuclear effects, so they're isotopical anomalous, and typically they show mass-dependent fractionation effects. So they have low initial Aluminum-26-27 ratio, and they also show low beryllium-10, beryllium-9 ratio. So according to Steve's idea, so the low initial Aluminum-26-27 ratio in these inclusions is the result of resetting. In fact, resetting is not such a simple process. You can reset if you melt the inclusion and then you crystallize different minerals from this melt. In this case, the aluminum magnesium systematics and beryllium boron will be reset. But notice that fun inclusions, they show these large mass-dependent fractionation effects. If CIs were melted during condor formation, So contours show complete isotopic exchange between the gas and the melt. So it means that mass-dependent fractionation effects will be erased and oxygen isotopic composition of CIs will become O16 depleted. So it means that this melting of inclusions could not have happened in the region where contours formed. Point number one. Point number two, you can avoid, you can say that the CI wasn't melted, but aluminum magnesium system was reset. But sorry, you cannot do that because CIs consist of different minerals, and resetting means it's a diffusionally controlled process. And different minerals have different magnesium diffusion. So it means that you can disturb isochron, but you cannot reset it. So what it means that we have to live with the fact that for some reason, fine inclusions formed with a low initial element 26-27 ratio. It's not a result of resetting. But now if you can go to my slides now.
So yeah, I'll take mine down. But Sasha, I actually think the CIs formed at 0.8 million years in the first place, not reset, it just formed.
I see. No, it's certainly a possibility. Okay, but let me show you like what is the problem with beryllium-boron system. So this is the graph from Fukuda paper. So what is plotted here? So the initial element 26-27 ratio for CI is along x-axis versus beryllium-10, beryllium-9 ratio along y-axis. As you can see that there is no consistency between element 26-27 ratio and beryllium-boron system. So there are significant variations in the initial element 26-27 ratio, but almost no variations in beryllium-10, beryllium-9 ratio. Or in some cases, you have inclusions that have canonical element 26-27 ratio, but much higher initial beryllium-boron ratio. So this is, if you would like to interpret element 26 and beryllium-10 as uniformly distributed, shall leave radionuclides, you shouldn't really observe these differences in distribution. So if the CI has canonical element 26-27 ratio, it should have canonical beryllium-10, beryllium-9 ratio, like 7 times 10 to the minus 4. But you cannot have element 26 poor CI and have element 26-27 ratio, which is 7 times 10 to the minus 4. But so here's another example. So this is the graph from Wieland paper. So they analyzed like 2 fun CIs and several non-fun CIs, which have canonical element 26-27 ratio. And as you can see that all these CIs have resolved differences in the initial boron 10 beryllium-9 beryllium-10 beryllium-9 ratio. And because we think at least what Steve said, that the initial ratio beryllium-10 beryllium-9 in the solar system was 7 times 10 to the minus 4. So if you know the initial ratio and the CI that we measured, it can calculate the time difference between formation of the CI or beryllium-boron fractionation and the initial solar system ratio. Like for the inclusion 2771, the time difference is about 1 million years. But if you compare element 26-27 ratio in this inclusion, which is 2.8 times 10 to minus 6 compared to the canonical ratio, 5 times 10 to minus 5, we find that the age difference is 2.6 million years. So it means that these ages don't match each other. It's called discordant ages. Now it's even more extreme example. So this is the CI from primitive CO chondrite. So it avoided any metamorphism, any alteration. And the CI is a condensate. It consists of minerals with the same condensation sequence as is predicted from the gas of solar composition. So you start from hebonite and condense crocite and melite, pyroxene, forsterite, and enstatite. So it covers the entire condensation range of different minerals from the gas of solar composition. It's uniformly O16 rich, so it means that it formed in the gas of solar composition. It avoided any melting. And beryllium 10 beryllium-9 ratio in this inclusion, but it was only reported in the abstract by Emily Dunham, is 15 plus minus 7 times 10 to minus 4. Let's say that it's about canonical, so 7 times 10 to minus 4. But if you look at element 26-27 ratio in this equation, it has nothing. So it's element 26 free. So the upper limit is 6 times 10 to minus 7. So now if you calculate the age difference for beryllium-boron system, it's 0 because it started with the canonical ratio. But in terms of element 26-27 ratio, it requires age difference 4.7 million years.
Yeah. So this is a great example. I'm going to interrupt, Sasha. This is a great example. And this is a demonstration of how pre-solar hibonite is making its way in. This aluminum 26 measurement is dominantly, the spots I believe are in the hibonite. And I think what you're looking at is pre-solar hibonite. And whereas the beryllium is coming from the melolite. And
I'm sorry, Steve. We also analyzed melite in this inclusion. It plots on the same isochrone.
Okay.
So there is no difference.
I mean,
I wish we had pre-solar hibonite or grossite inside CI that has canonical element 26-27 ratio, but we don't have the example of this.
I mean, this slope is mostly dominated by the grossite and the really refractory phases. So look, it gets into the weeds, but all the samples where you can infer a very tight upper limit on the aluminum 26 are these very refractory phases only. And even in individual inclusions like this. And getting back to the other fun CAIs, the only non-hibonite dominated fun CAIs you can play this game with that might have a distinct beryllium 10 and aluminum 26, there's only 2. And they're CMS1 and KT1. And both of them are consistent with formation at 0.8 million years in both systems. It's not there's a lot of air bumps. But,
yeah, I understand.
But they're consistent with a late formation. Yes. They're not discordant.
I understand. But again, this is the question is how to interpret low initial element 26-27 ratio.
Yeah, I think you're looking at a pre-solar signature.
Yes. But anyway, in principle, there is a test of both ideas. So what we need to do is to measure beryllium-boron isotope systematics in CIs that lack element 26. Steve already explained that this low initial beryllium 10 beryllium 9 ratio is observed in fun CIs. But there is a special group of meteorites that contain very pristine refractory inclusions, the so-called CH chondrites. And 85% of CIs and CH chondrites don't have element 26. So all we need to do is measure beryllium-boron isotope systematics in these CIs. And there are 2 papers where reported initial beryllium 10 beryllium 9 ratio in CIs. So they both showed high initial ratio, but they probably don't go through the test that Emily Dunham and Steve applied to basically whether we can use this data or not. But I'm not arguing against this. All I'm saying that we need good isochrons for the CIs. But if you find high initial beryllium 10 beryllium 9 ratio, then irradiation is required.
No, well, if it's very high, yeah.
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 Yes.
So let me here stop you and then ask if there, from the audience, if there is actually a question or clarification from here. So there is a question by Neil Turner. Could you plural say more about hypothesized places where the irradiation altered the beryllium? Yeah.
I mean, if there's energetic particles like MEV protons from solar flares, but they are not going to penetrate more than about 10 grams per square centimeter of material into the disk. So they basically irradiate the skin of the disk. Emmanuel Jacquet did account for this and still found a high enough beryllium 10 abundance if you mix that material into the disk. A lot of models out there don't really consider how much of the material is lost, just irradiating the skin of the disk and ionizing hydrogen molecules. It's a very inefficient mechanism.
And Qingzu has a question too. If beryllium 10 is heterogeneous, does the delta T calculation based on beryllium 10 has any meaning at all?
It would not.
No, it doesn't. That's exactly my point, is that if you make assumption that beryllium 10 beryllium 9 ratio was uniform at 7 times 10 to minus 4, then you have to interpret beryllium boron isochrons chronologically. So then you can infer the age difference between formation of CIs with different initial ratio. But if this is true, then, and if aluminum 26 is uniform, the ages must match each other. But the data that exists right now, they're controversial.
Yeah, as long as you don't look at Hibonite, I think they do match, and or the refractory phases. And I do interpret the beryllium 10 chronologically.
No, it's a matter of interpretation. But as I said, that there is a good test of this idea.
Except
What
that
would be the perfect sample would you like to have?
No, we have CHCIs, so they and actually many of them aluminum 26 free, and they consist of mellites, so they're not Hibonite or grossite or corundum. So they are measurable for beryllium boron isotope systematics.
So yeah, unfortunately, in a lot of the pre-solar materials, the beryllium is only coming from the solar nebula and should be canonical, even if aluminum 26 is not. So we have to be very careful about those tests. And I wanted to agree with Jinshu that chlorine 36, I think we all agree, probably did form by irradiation in the solar nebula because it had to form late after the gas has dissipated, so that you're not wasting all the energy of the energetic particles ionizing gas, and you actually irradiate the gas and form chlorine 36. And Sasha has amassed a lot of evidence that you have to have irradiation forming chlorine 36 late. But late, and it's the only one. And it got into the CAIs via water and aqueous alteration on the parent particle.
I mean, there is also paper about vanadium 50, but I didn't want to go into this.
So if you suggest to those of us who are interested, please send us the link. I will actually share with the people in our website or in here. So there is a suggestion that we should continue this debate next semester again, because we didn't talk about beryllium 10 in time, and chlorine 36, definitely I would like to hear about that too. So if you can, we'll schedule another one next semester for second part of the debate. And there is a poll that I wanted to actually hear from you. At least there are 36 of you. Click the Slido link and write down the word that you would like to, the questions asking. I hope to see that some answers for that. So Steve and Sasha, if I can give you both of you, each concluding kind of sentence statements. Could you go ahead? Sasha, would you go ahead first, or Steve?
I can go first. I think these three mechanisms that were listed on the first slides, on the last slide by Steve, they're all correct. So we have inheritance of short-lived nuclides, we have radiation, and we may have evidence for late addition of aluminum 26 from the wind from Wolf-Rayet star. That's my understanding. It's not simple inheritance.
And my stance remains that inheritance is by far dominant, and there's little evidence at all, and it's astrophysically hard to inject material. There was a radiation late in the disk to form chlorine 36. I don't think it had any significant bearing on what CAIs formed with, or what the earliest solar nebula formed with, or what most of the material in the solar nebula had. It was a small effect later. And I think the aluminum 26, it remains to be seen. There's a lot of work to be done, but I think the aluminum 26 free stuff you're looking at is their survival of the most refractory pre-solar aluminum 26 free material, and that's it. And it's chemically heterogeneous, but homogenized pretty early in the solar nebula. But it always had aluminum 26.
Okay, so any question from the audience?
And I got to go in like 2 minutes.
Yeah, so thank you both. And I have a lot of questions, but I think I'll ask questions in round 2 or personally. And this has been really fun and a great read, and it was fun debate. And we will have a second round next semester. And thank you all for sticking around. And please do answer the question that I will appreciate it. Steve, thank you very much for calling from courthouse. And good luck today. And Sasha, thank you very much.
Yeah, thank you, Steve. Thank you, Serena. And thank you, everybody, for attending this seminar.
Yeah, thanks, everyone.
Yeah.
That's fun. Thanks,
Thank you.
Sasha.
Let's say thanks to the speakers today. And I'll post the video in our YouTube channel. Thank you very much.
Okay, bye.
Bye.